who want to learn more about the real potential, the real power of bioremediation. And I will guide you through some information and some three projects we've been conducting recently. But let me just first show people who can be contacted depending on the country or the continent you're located at. This will also be shown at the end of the presentation. So these people can be contacted for further information. First, just 2 or 3 minutes on who is GreenSoil Group. We're a specialized, innovative and international remediation contractor. We're founded in 2016, but most employees, which are about 30 now, have more than 15 years of experience on bioremediation. So let's say that most people have been growing in their career on bioremediation on real project experience. We have offices in Belgium, the Netherlands, Brazil, Chile, and Italy. And we have necessary certifications, ISO, VCA, but also country-specific if we work abroad. We're in innovation and knowledge-driven, which means that as a small but specialized bioremediation contractor, we put a lot of effort in R&D. We have quite some resources in R&D. And we also focus a lot on unknown components or emerging contaminants. And we do that from a pragmatic point of view, in which we differ from like university or purely laboratory point of view. So if we do a lab study or a feasibility study, we will translate that in full-scale remedial options that we also may put further into a contractual agreement. Sustainability, I think, is an important focus for GreenSoil as well, in which, of course, bioremediation has a big focus. We do want to explain clearly that we're a contractor, although we're knowledge-driven. We do act as a general contractor, so we take on remedial contracts as well for in situ and on-site soil remediation, groundwater, soil vapor treatment, and or not demolition works. So we can offer a total concept. And it's basically the link between the subsoil and treatment systems, really, pragmatic knowledge of implementing knowledge and experience that makes the difference in the projects. We would say we're client orientated because we're small, but also because we do want to deliver result-driven contracting. So we always try to get the best outcome for our clients, which could be both a time and expenses contract, but also a risk-based contract where we provide a guaranteed outcome. Of course, that will ask for an intensive involvement of both of all parties involved, of all stakeholders, being the consultant, client, and the authorities. And we're currently working in 12 countries on international projects, and that growth internationally has to do with two aspects. For one, we're specified in bioremediation, which is, I think, growing in interest. But it's a niche market, and as a small but very high-skilled team of people, we can do these projects fairly easy abroad and fill in gaps of knowledge in a specific country. On the other hand, as we're a general contractor, we often use local partnerships to conduct the works, and for us, it's more like being able to conduct from the beginning till the end, from the initial design to the end of the remediation project. That control is very important to us, and we therefore rely on strategical partnerships either in Belgium, the Netherlands, or any country. So we don't invest in materials, they're available. We invest in experience and application and project control as a contractor. Often it starts with questions from clients on different either known contaminants of concern, like chlorinated solvents or BTEX, which are quite well known these days, what is possible or not, to very new components. And you can see some of these projects we've been doing throughout the world on different components. And often by the beginning, we also don't know what the outcome is, if it's biodegradable or not, to which extent. But it can be done by a small feasibility study or a larger scale pilot test. And if then comes out that biodegradation is feasible, we turn it into prospects of a full-scale remediation. And you will see that in this slide, a lot of the projects indeed come back as full-scale remediation projects. And often for us, we try to find solutions where sites have been long time struggling on finding a solution that could work, that can be implemented, often in very strict chemical conditions. And actually, bioremediation is one of the softest techniques in situ that can be implemented in difficult conditions. So you see that some of these sites then one-on-one come back in a full-scale remediation, which of course is our aim to provide full-scale remediation options. But that's a bit about GreenSoil in short. Some of us are clients who joined, some don't know us. So I hope that this puts GreenSoil a little bit into a good perspective. But why biology? Most people know biological treatments from wastewater systems already for decades. And actually that has been implemented already a long time. If you look at a conventional wastewater treatment plant, the first step is most of the time a biological step to remove the bulk of the contamination. That was before biology was applied in wastewater treatment systems. That was not the case. The reason why that has been implemented is because it was very costly to conduct chemical or physical treatment techniques to very high flows or very high bulks. So biology in itself becomes more cost effective with higher contaminant mass, with larger volumes, with larger concentration levels. And that's something we often have to point to, because often the reverse is thought of. There are a lot of prejudices about biology in soil remediation or groundwater remediation, that it's limited and that it's only for low concentrations, that it takes a long time. Well, we strongly say otherwise, and hopefully we can prove that with our project examples. But in effect, if you look at contaminant mass, the cost, and in the left graph, you see that the cost structure of a biological remediation is completely different than conventional techniques. Once the system is installed and we create the right conditions, these microorganisms we're talking about degrade for the same money as we say large contaminant mass or low contaminant masses, because if they have the right conditions, they grow exponentially. And that's why your cost is relatively low once the conditions are set and your infrastructure is set. And if you then end up in a contaminant mass that is 3 times higher than initially estimated, it doesn't result in a 3 times higher cost on your project. So in basis, in structure, the cost is different in a bioremediation project than in conventional projects. If you look at then sustainability and footprint issues, you see that compared to conventional techniques like soil washing or thermal treatments, that we speak about a 10% at the maximum of CO2 production in bioremediation processes. And of course, that is because these microorganisms have developed enzymes that facilitate these processes of oxidation or reduction by many millions of years. So they are just very good adjusted and have become very cost efficient. Now, it's all nice talk, and of course it's nice to see many people interested and seeing purpose or seeing prospects in bioremediation, but what we want to show is what can be achieved. And the first project is a project we've been doing in Belgium, where we have cleaned a heavily impacted site with xylene, where we have treated soils, groundwater and soil vapor in a biological way on site. It's a Civiso site, and it's a former production site of medical equipment, where actually xylene was used as a basic component. This project has been conducted in building team construction, so it was a guaranteed outcome project where consultant and contractor have been appointed by the client in one contract. And basically the main contractor in this case was RSK, and they together with GreenSoil we proposed a total outcome solution, and you will see that even the type of contract can define and can drive innovation to some point, and this site is actually a nice example of that. But to start from, in a nutshell, what's the contaminant situation? You have the tree source area of a heavily polluted area. Groundwater fluctuates quite heavily between 1 and 4 meters. So you have like L-napple of xylenes and BTEX that has been smearing out until 4.5 meters of depth in very high concentration levels. In soils, we talk about 10,000s of milligrams per kilogram. So that's very high. And underneath that smearing zone, there's a highly loaded groundwater concentration plume, up to 10 meters below groundwater level. The difference between these zones is just in soil concentrations. In groundwater, it's saturated. We're talking about 10,000s to 100,000s of microgram per liter of xylene. But if you go to the lower part from 4.5 to 10 meters, you see that your soil concentrations are in line with the groundwater concentrations. So there's little sorbed phase in that fraction, but still it contains 7 tons of contaminant mass. But the bulk is in the 76 tons at the first 4.5 meters. What did we propose is to treat these two zones actively, because then you have about 98% of the contaminant mass actively treated, and then the deeper plume, which has only low concentration levels, will be depleted and will be degraded by natural attenuation. So how do we do that? For the first, here it's mentioned 3.5, but in the end it appeared to be 4.5 meters, we have excavated the soils and we've put them in active biopiles at the site itself. If you look at the picture at the right top, you see that it's very close to the active plants. So there were quite some measures for emissions that we needed to do. But one of the things to maintain our emissions is that we don't blow air through the biopiles. We don't turn them around. We build them up and construct them on top of an SVE system where we extract air from the outside through the biopile. And not only does that is that biopile then continuously under pressure, which reduces the emission. It also is very beneficial because you continuously provide oxygen, fresh air to the biopile. Of course, this is very simple in principle, but there can go many things wrong when you construct these biopiles. Homogenization, nutrient resourcing, right condition control, these parameters of moisture, temperature, they're all very important when you operate and you want to speed up these biopiles. So in principle, that's for the unsaturated zone, and for the smearing zone, the technique we apply. Why do we excavate them and put them in biopiles and not treat them in situ? Is because of these high soil concentrations and because of the mass of 76 tons we need to treat. You need a lot of air supply to the microorganisms so that they can treat these huge tons of contamination. If you go deeper than 3.5 or 4.5 meters, you have basically a very heavily impacted groundwater contamination, but the oxygen required is much less. And in a compacted soil, like these from 3.5, 4.5 meters, you can provide that by a system that is shown below. It's a biosparging system combined with a recirculation of groundwater. We actually try to make a big washing machine of the subsoil by extracting and infiltrating groundwater. We clean it in between, above ground, in between with a bioreactor, a groundwater treatment system. And in between that separate recirculation system, we put in biosparging filters. This is not an air sparge system because we don't want to blow out the contamination into the unsaturated zone. It's a very homogenized, specific biosparging filter that diffuses as homogeneously as possible the oxygen throughout the whole aquifer. So basically, these are the two concepts we use to treat these two different layers in the soil. Now, focusing on how we do the on-site land farming and how we built the biopiles, we actually construct preferably the biopiles at the location of the contamination. Why? Because if we can excavate and immediately build up the biopiles, we have limited transport movements at the site as well for emissions as costs. That's preferable. It also means that the time frame that you have open soils is very, very limited. And it means that given that you have a very highly impacted groundwater that you also need to treat, that leaching out from these biopiles, which is most often very limited, but if there is some leaching, that you can capture that with your in situ biosparging system. If you, of course, build up a biopile in an area that is not impacted, we will put a liner and a cover underneath the liners. Be aware that we don't put liners on top of the biopiles because that is really not good to do to get air into your biopiles. So given that it's under pressure, there's no emissions. Once we put the biopiles in its place, we turn on the system, you don't have any smell at all. After half an hour, it's gone, which is important. So basically, we can do that at the same moment, and we do it in very short lanes. So we shift up gradually throughout the source area by excavating, turning them around into a biopile and putting them on, and then proceed area by area. Of course, you've seen that the groundwater at this site varies between 1 and 4 meters. It's a highly permeable aquifer. It's a glauconite sand aquifer, which delivers a huge amount of water. Even at these small pieces of land farming that we do, we need to extract groundwater levels so that we can excavate until the bottom of the smearing zone. We have built a biological water treatment system of about 20 to 25 cubic meters per hour, which allowed us to reduce groundwater levels till 4.5 meters for an area of approximately 10 meters by 30 meters. So even if you would want to excavate this area in a hole, it's impossible because of treatment capacity. So this water treatment plant is being used both for the treatment of the extraction, the water extraction during the excavation and biopile buildup, as for the in situ biosparging treatment system. Important to know is also that biopiles cannot be constructed underneath the water table. They need to be built up above water table, otherwise you cannot aerate them. So we need to turn around clean soils, put them on the bottom, and treat the heavily polluted soils in above water table in these biopiles. And this graph just shows you also what is capable with bioremediation, because you can see in the first phase we had relatively low concentration levels. It was a less impacted area that we first treated. And you see that we have concentration levels varying between a couple of thousands and 20,000. We could treat those fairly easy to less than 10 micrograms per liter, which was the discharge limit, on a biological way. But then we started in the second phase with the really highly impacted concentration levels, and you see that you go up to 120,000 micrograms per liter. If you then reach a removal efficiency of 99.9%, it's still not enough to reach the limits of 10 micrograms per liter. So you see also in the beginning that we had some issues with the discharge limits, which represent a couple of hundreds micrograms per liter. The way we look at it then is that what we did is, after the biological treatment technique, we put a polishing step, which consisted of a conventional stripping tower. And a stripping tower is actually a very good polishing step because it's effective for low concentration levels, but it doesn't consume a lot of activated carbon from your air to be treated because the load is minimal. Again, we remove the bulk of the contamination in this water biologically, and we polish it with conventional techniques. And then stripping in combination with activated carbon becomes very efficient. So we try to take the best of each technique and combine that in a cost-efficient way. So let's say we have lowered the groundwater table, we have built up the biopiles. What happens then is that we see that actually these biopiles, if you control in the right way all parameters, you see them increasing in temperature. You see that carbon dioxide is high in your effluent. You see that oxygen is depleted because it's consumed, and you will see that the contaminant front will go from the outer skirts of the biopiles to the inner core. And at a certain moment, you will see in your extracted air that you treat, that the parameters change, and that what has been broken down in mostly has been biodegraded. And that moment allows us to say to the consultant or to the RSK in this project, okay, now it's time to take samples. Now we think we're close to the end. We don't need weekly control because we can see at our air that we extract from the biopiles how far we are in the process. And what's apparent in these biopiles, and if you look at the different concentration levels where we started from, is that at about the same period, even if it's very contaminated or less contaminated, you see that in a period of about 60 to 70 days, you get below the remedial standard, which was about 379 milligrams per kilogram. And that is because the BPEX, they're easy bioavailable. So there's no limit on the exponential growth. It's readily available. As long as your conditions are well, they will just explode. And you see that if you start at 4,000 or 500, it takes about the same amount of time to get to the end, which was a surprise to us because, in fact, we used to do this for TPH soils. But TPH is much more absorbed to the soil matrix. It's not readily available. So your limiting factor in biotreatment of TPH soils is the bioavailability, not the biodegradation as such. So therefore, the slope of the degradation curve will be much more a linear curve because the microorganisms are limited in growth due to the limited transfer from pure product absorbed to the soil to a dissolved phase where it can be broken down. But this is one of the rare projects where BTEX concentrations are so high in concentration. So we were kind of surprised that in a relatively short time of less than 2 months, 2 to 2.5 months, that these concentration levels decreased 90–95%, and that they all took the same time. But we were also surprised by the fact that the last ORD depot did not show the same results. And the reason for that is that it was constructed, it was the last one, in very wet conditions. And we needed to decide to wait until the winter time was left to continue, or we took the gamble to also put them in depots, but they were constructed too wet. And we saw after 2 months that the concentration levels did not drop. So also at that moment, we see that something's wrong with the biopiles, and we decided to turn them around and build them again on completed biopiles so that they could be in more dry conditions operational. And at that moment, you see that the same curve responds to what has happened before. So we do see changing things, and we do see differences. It's not a matter of not wanting them to have on a remediation project. They always come at some point around the corner. The matter is that you can adjust and that you have techniques and solutions to adjust accordingly. And one other aspect that was surprising, and this is why I want to show that also the type of contract defines innovation, is the air that we needed to treat. As I said, we used to do these on-site land farming for TPH soils, and you have very limited volatility. There's only limited load in your air that you extract from the biopiles that you need to treat. So conventionally, you just put a small activated carbon vessel behind it and you're done. Especially when the biopiles become active, you only get CO2, but in the initial phase, you do get some PIDs in your some load in your effluent air. But for this BTEX site, given the very high soil concentration levels and the volatility, we were surprised because we had exhaust gases from our biopiles up to 7,000–8,000 ppm. Of course, if you then use activated carbon, you run dry on your project finances very easily. So after 2 or 3 weeks, we realized, okay, we have really a problem with the amount of activated carbon we need to use. And then you sit together with the soil expert, with the client, because this is a one contract thing, and you start thinking, what is the best outcome to get out of this problem and to make it manageable? And one of the ideas that our project manager had is, well, we have had this first phase that was less contaminated. We have biopiles that have been treated. Can't we just use them as large compost filters and send air coming from other biopiles right to those, in a reversed way, to those completed biopiles? We will cover them up with a liner so that there are no emissions, because then you blow air through these completed biopiles, but we balancing them out. And I mean, if this is so contaminated air, wouldn't we get kind of a removal efficiency by doing that? So we did that, and we sent air of 7,000 ppm through these reversed biopiles. Of course, we needed to re-engineer these biopiles so that they could act as a butt, as a compost filter. And what we saw is that we had a removal efficiency of 70–80%. Not only that happened, by sending this very dirty air, also the residual contamination in the soils was reduced from a level below 379 to non-detectable levels. So in terms of circular economy and in terms of sustainability, we were able to clean up very dirty soils biologically to meet standards. We could reverse them into air treatment systems, and by treating air, we could clean up the soils to levels non-detectable. And we could reuse the soils at the site as clean soils. So that was, and the reason why I say this is a game changer in our approaches is because if this was a time and expenses contract, the bill would have been paid by the client, because you would then normally say, well, client, I'm sorry, but yeah, we underestimated the amount of activated carbon necessary, and it's 10 or 20 times as much, and you will have to pay a couple of 100,000 euros in extra. As we had a guaranteed outcome result for a lump sum amount, it was our problem. And within the building team, if you put the right people and the right knowledge together, and you both have the same incentive, then you can get to very innovative solutions. And that's what happened here. In addition to the bed, we also installed a bioscrubber. Sometimes this bed and compost filters, they take a lot of space, and you don't always have that space. We also have, we are developing a bioscrubber, but the problem with bioscrubbers is that it's in O&M, it's quite extensive. So you need a lot of resources to be able to operate them. But this is an automated bioscrubber where you have little balls in it that are being pumped around, and actually the air is being sent from the bottom to the top, and water is being sent from top to down. And in that tube, then the biology starts growing, and it attaches to these balls, this carrier material. But the carrier material is being the biology is being loosened because of the mechanical shoveling of the balls in this pump to pump them around. And then the sludge is just being captured in a vessel and pumped over to a container unit. This is a pilot test installation, but we had an efficiency of about 55%, and it's proved that it can work both for water and air at the same time. We're now changing over to a full-scale system where we will change a stripping tower into a full-scale air treatment system, where we are positive to get similar removal rates as within a compost filter, but where we save a lot of surface area, which could be interesting in chemical plants, for example. Finally, we send it through the compost filter and to a GAC filter, and we could save up to 95% of granulated activated carbon consumption by just breaking it down in all phases, being soil, groundwater, and air. So that's about the biopiling. Then we go further down for the in-situ biosparging system. That's as explained by recirculation groundwater and doing a separate biosparging system in between. Now, this is the main area that has been excavated, and it was phased out to do first the biopiling and then the in-situ biosparging system. But as we started with these works, it was found out that the sewer systems from these active production plants also leaked significantly, and that actually an additional area was found with high concentration levels in soil and groundwater, but that was not suited for excavation. So there we installed also a biosparging in situ system. And this is now has been monitoring. There's wells every couple of meters to monitor. And we have been operating this system for approximately 1 year now. And you can see in the left bottom graph the evolution of the xylene concentration levels in groundwater. And we get removal efficiencies in between 70 and 100% or 99% after 1 year, with intermediate results after 6 months that lie a bit higher. The fact that some take longer has to do with the amount of soil contamination, so the amount of absorbed contaminants in the soil. The more absorbed soil contamination, the higher the mass, the longer it takes to deplete certain areas. On the other hand, we were happily surprised with the fact that for most areas, you can also clean this up in terms of 1 year or 1.5 years approximately for remaining areas. So I would say if you can show for these type of contaminants like BTEX that you can clean soils in 2 or 3 months maximum, and in situ in a period of 1 to 1.5 years, 2 years, I would not call bioremediation slow or for limited concentration levels. So this first project gives you an idea. It is a bit specific because, of course, the site and the type of contamination is very suited for biodegradation. And we cannot always do on-site treatment of all aspects, soil, groundwater, or air, soil vapor. And one of these second project we want to show is that we also combine it with conventional techniques. In this case, we used an SV system because groundwater was at 11 meters below ground level, and actually then in the unsaturated zone, it's very difficult to get good bioremediation ongoing because it's not humid enough. The humidity is limited. But what we then try to do is combine that conventional technique with actually biological above ground treatment systems. And so this in situ system is at an active highway gasoline station, where we installed an in situ system composing of 44 SVE filters, 4 pump and treat wells, and a biological water treatment system. And we proposed to the client to use a compost filter, an automated compost filter and a GAC, because there were quite some tons, approximately 12 tons of contaminant mass was present in this unsaturated zone. And the reason for that can be seen in this graph. If you look at different air treatment techniques, you could combine, we have combined and calculated that a compost filter to take out the bulk and a GAC filter for activated carbon for polishing step is less susceptible to variations in costs and in load, in contaminant mass, because the blue one is a simulation of the cost if you have a 25% lower contaminant mass than initially calculated. The 12,000 was what we calculated of contaminant mass, and then you have the plus 25 scenario. If you look at the slope, you see that it's a flattened slope, and with increasing concentrations, it becomes a bit more expensive, but much less than with activated carbon only. And that's very important to notice, and that's because you have this buffering capacity of the bioremediation for high concentration levels. If you look at the CATOC system, a thermal remediation, we would have, in this particular case, would have been much higher in cost, but that effectively becomes lower in cost with higher contaminant level, because some of they can run then a bit autothermic. But they were significantly more costly than the other option. So the client agreed to make the combined compost and GAC filtration for this site. And actually the compost filter is a 40-foot container with an humidifier, heater, nutrient dosage system, and automated process control. So it's not just a container filled with some wooden chips, because that's not working. The conditions need to be right if you want to get high efficiency. We had an ATEX, we were at ATEX level at 100 plus LEL working, so we need to have specific extraction units, and it had an ATEX blower of 1500 normal cubics per hour. The GAC filtration is a polishing step, and it's 2 container units of 4000 normal cubic meters per hour. Here you can see some of the effects of the biofilter, and you also see that at some point your cost effectiveness of the pre-step of bioremediation becomes limited. Of course, there is an operational cost of having a bioremediation step, and if your load becomes too low, then that cost is higher than if you only use granular activated carbon. But if you look at the beginning, you see that we're at very high levels of incoming air, and you also see at high bulk mass coming in. In this period, about 70 to 80% and higher removal efficiencies of the bioreactor or the biocompost filter have helped to lower down the activated carbon to up to 80% of costs. But at a certain moment, you see that you get very low concentration levels in your SVE system. And then it was decided that the pre-step, the bioremediation step, was going to be left out, and only a GAC filtration was continued because it was cheaper, only the GAC filtration. And that's where you see when the GAG filter works only, the biofilter falls away. So there's no more biofilter. So in this graph, it's shown as 0 efficiency, but it's just gone. You also see that you have a limited rebound effect that has to do with the shutdown to some extent, but also because we reduce the amount of operational wells as we go on. And we remain stuck to some 8 wells that keep delivering high loads. And these are shown in this graph. So we're basically only polishing the in situ system with 8 filters that keep on delivering higher flows up to 2000 ppm, of which we also think that there's still some pure product left in the unsaturated zone. So it only takes time, but it's a limited amount. It's only 8 out of 44. We had about intermediate SVE wells that gave quite high concentration levels, but lowered during the operation to levels of 0, that also have been gradually shut down. And we had very limited SVE wells at the outer skirts of the source area that could be turned off in a quite early stage. So basically, this shows that even if you don't conduct the bioremediation in the soils, which we prefer, that still biological treatment techniques can help to manage your financial risks to a large extent. It also needs to be noted that we had significant higher contaminant masses than originally thought. So if you look at this picture, actually the green area was more like the orange area that we were in contaminant mass. So going from completely doing biological things on-site, in situ, to a project where we have an above-ground application, we also have applications where we don't have treatment systems, where we only focus on things need to happen in the subsoil. Projects where we want to create the soil as the bioreactor. It's basically, for most in situ remediation projects, the key factor of success of bioremediation is to create those conditions in the subsoil that 90 to 95% of the contamination is broken down, not above ground, but into the soils. That's our main principle. The only thing is, soils are a bit difficult to create good stable conditions. In an above ground water treatment, you have water coming up, you see an influent and an effluent, and it's manageable. You can fairly easy change conditions and optimize them. In soil, it's more difficult, but it's possible. But you have to take into calculation geology, hydrogeology, chemistry, biology and engineering together. And that makes it a very difficult area of expertise. But this project actually is a chlorinated solvent project where we only use the microorganisms in the soil to degrade the contamination. We do use the system always for chlorinated solvents. We don't use above ground treatment systems because for 2 reasons. One, stripping out the contamination is not good because the organisms that needs to grow, they need the chlorinated solvents to grow on because they use them as electron acceptor. And 2, above ground treatment systems of chlorinated solvents take a lot of volume because the degradation rate is much lower. It takes a longer time. It takes about 8 hours for an anaerobic process to degrade half of the contamination versus an aerobic one. So if you want to treat 1 cubic of water, you only need a half a cubic of treatment capacity in an aerobic application, but you need at the minimum 8 cubics for above ground treatment. So practically it's impossible to have a bioremediation system above ground that is manageable in size. And it's not necessary, so that's basically what we do. The way we build up the microorganisms in the subsoil is similar to the previous project at Belgium with the BTEC, with the xylenes, is we recirculate groundwater. We want to get the aquifer mixed up as much as possible. And by doing that, we dose directly a nutrient source, and in this case, we have our own, Dihalogy S. Don't look it up at the internet. It's not commercially available because we do not believe that commercial products solely can get you to an end solution, because any product can work or work not. The way you apply it is as important as the product itself. But anyhow, we recirculate and we dose the Dihalogy S to the necessary levels that the aquifer require. In this particular case, it was at an active chemical plant in France, and there was highly contamination at different levels, which was linked to the soil constitution, to the geology. You had DNAPL concentrations in a loam smearing zone, and then you had two highly elevated areas at between
Hi all, this is Jan van den Holland, one of the colleagues of Rogier. Seems like connection with Rogier just dropped. We'll get in touch with him and hope to get this back online as soon as possible. Okay, seems like Rogier is getting back online. Bear with us for another minute, please.
Hello, I'm back online. Can everybody hear me?
Okay, Rogier, nice to have you back.
Sorry, the internet was hit by the coronavirus, I think, shortly.
Are you able to put the presentation back online, Rogier, or?
Yes, I'm able. Just a second.
All right.
It should be there.
Okay, here we go again.
Okay,
all right.
Sorry for the small interruption. Internet just failed a little bit. I was just explaining about the regions we need to look at it, and it was basically very highly DNAPL concentration levels at 3 depths. We did a pilot test where we also wanted to use heating, because this geology, it's a loamy, very heterogeneous geology, and actually the desorption and the demobilization, the mobilization of the contamination is the most difficult part. It's stuck to the soil matrix, and the CVOC intercalates in the most small pores of the soil. And the thing why you always get a rebound when you do physical treatments like pump and treat or a multi-phase extraction is because you just cannot physically remove those stuck soil concentrations. They are absorbed, and the only thing you do is extract clean water from the outside through your pilot test zone, but there's no contaminant mass transfer. In a bioremediation project, it's different because it's based on changing the diffusion equilibrium. Instead of removing them chemically, physically, you remove them chemically, because what happens when you put nutrients into the groundwater in these soils, they keep the concentration levels of the basic components to very low concentration levels. So your diffusion coefficient between the salt and the groundwater phase is very large. And actually that principle drives the DNAPL droplets that are intercalated. It drives to deplete them out of the soil to the groundwater phase. It's a chemical diffusion shift. And if you can continue to keep these conditions of high degradation for a longer time, you see that you gradually deplete the chemicals out of your soils. And why do we do the heating? Because heating accelerates not only biology, but also this bioavailability, this mobilization. Heating up things makes them more smooth. It's like jam. If you heat it up, it becomes less stucky. That's also what heating does. So given the difficult geology, we also did this thing with the heating. There was one surprise, the heating process, it did work out. But due to some technical issues with the groundwater extraction, it's very fine sand that impacted our pumping. We were in the beginning limited in flow that we could recirculate, and so the heating up of the extracted groundwater and the reinfiltration of that heated water was limited, so that we only saw at the first 2 or 3 months a limited increase in temperature, which we could enhance significantly when we changed over to another pump regime, to another way of pumping that was less impacted by the fines. And actually, as we did that, we could increase the groundwater up to 26 degrees, close to the injection well. So we did create an area with increased heating. But the thing was that it was too late. And why? Because all contamination was already degraded within 3 months. And that's actually what we see here, is that if you look at the different monitoring wells and the injection wells, the pilot test is set up with 1 central extraction well and 4 injection wells in a square, is that we have follow-ups at different distances, the evolution of the concentration levels. And in this case, we started with, for example, in the closest monitoring well, with concentration levels of dichloromethane up to 200,000 micrograms per liter, and of 1,2-DCA of about 160,000 micrograms per liter. And we also monitor the end product being ethene of the degradation. And you see that from approximately June until the end of the summer, August, we had an exponential decrease. Again, biology can go very fast as long as the contaminants are bioavailable, which in this case was the case. We see that the further you go away, deep well 7 is in between 2 injection wells. This is where at the latest point you will see a result. You see that the shift is delayed a bit. It's going just after summer, which is normal, because if you want to flush this whole system, you need to have the time to extract and reinfiltrate, so that it's a closed cell. And that's what you can see at this moment at deep well 7. You can see that it's a closed well. A similar thing happened at deep well 15.01, which also showed a later change. But if we see in our extraction well also this decrease, this depletion, then we know that the whole area has been cleaned up. And if you then expand that to a full-scale application by monitoring the different areas, the different extraction wells, by monitoring these wells, you can fairly good predict how far you're in a certain area ongoing with your remedial, with your remediation actually. This is a slide I'm not going to discuss because I would like to refer to the next seminar of our R&D manager, John Deck, who's a microbiologist and knows much more about it. But we also always monitor molecular analysis and from a molecular biology standpoint, evolution. The only thing we can say about this is that indeed the ones who can degrade the 1,2-DCE and dichloromethane increased significantly throughout the pilot test. We also need to state that prior to the start of the remediation, that natural degradation was already at relatively high levels. So this was a site where degradation was already pretty ongoing, but it was just not enough. The nutrients were lacking to complete it. And then you can see that if you add it, and you add it properly with the right nutrient source, then it can jump on. The main conclusions for the pilot test, and it's a bit short notice, all of it, but is that basically the biology did very good, but we had some problems with limited mobilization of the phased heating, and we had some additional more engineering things we needed to include in the full-scale system, which now is operational from 2018. It's without heating because it has proven not to be strictly necessary, and then you don't have to make that cost. We have calculated theoretical consumption of DHaloG as for the full scale. We have been applying a factor 10 more because you always have losses, and it has been implemented in quite restricted conditions, but it's basically quite manageable and under control. So this is now running for a couple of months, and also on the full scale in the 3 geological layers, we're seeing the same things happening as in the pilot test, which basically is only where you only need a recirculation system and nutrients and knowledge of the aquifer and how to combine them to get to a good outcome of bioremediation. Of course, if there's heating and DNAPL removal that we can also do as a separate technique, has been involved in these treatment units, because often it is a combination of different techniques that we need to apply to get to the end result. But in this case, so far, it has not been shown to be necessary. So these are some more slides on the O&M, but it's less of an interest at this stage. It's more engineering-wise. So I've run over time, but I hope this was interesting. And for the people who have some questions, I'm happy to respond. And otherwise, I would like to thank everybody to participate, and would very happily refer to the upcoming events the next 2 weeks. There will be other people from a different perspective presenting projects. Next week it's more from a microbiological standing point. The week after it's more from like a brownfield development standpoint. But both will also, the main thing is that we clean up these sites in a biological way. So,
okay,
Michaela, we have some questions.
Thank you.
Feel free to leave if it's too late, but feel also free to continue if you think it's interesting.
We got a few questions. We can go through them quickly. Mm-hmm. Could you give an overview on pricing per tons of the contaminated area per contaminant and time schedule compared to other methods? Mm-hmm. I guess refers to biopiles.
Well, yeah, it depends. It varies depending on the type of geology and the type of contaminants. And in general, I would say we would end up in between 10 and 20 euros a ton, while conventional soil washing would be in between 25 and 45, depending on the fines. And thermal these days, yeah, you get up to about 80, 85 euros a ton. But it's a difficult comparison because in the project we included all treatment systems, above ground treatment systems for air, for water are also included in that tons price.
Okay. Is that sustainable to use GAC in bioremediation, and what is the end of the contaminated GAC?
Well, granulated activated carbon, in our opinion, is a very good product for polishing steps because it has a very good efficiency at low concentration levels. Is it sustainable? In these type of applications, if you can limit it, yes, because you don't put the the vapors into the air, into the outside. For high loads, I think it's less sustainable because they need to be regenerated, they need to be burned, the contaminants need to be burned, so your carbon footprint is also much higher. In basis, I would say whatever you can biodegrade will always be much more sustainable and lower in carbon footprint than any chemical process or a thermal process. It's in basis like that. Okay. Last question. In what scale a bioremediation is not feasible based on compounds nature and subsurface structure? I would say there are some, of course, there are limitations to bioremediation. In heavy clays, you probably will be limited in the bioavailability because they are very stuck. On the other hand, often in clays, the amount of contamination is limited to the unsaturated zone and where it has been leaking out. So there you probably would rather look at excavation. You rarely see at stiff clays from the top, you see big plumes arising. From a scale point of view, it's always applicable. But of course, the higher the volumes, the contaminant mass comes, the more profitable the investment of the infrastructure becomes. I would say that if you have a small private oil tank of a couple of 1,000 liters and you have a small leak, you will not treat the soils on site. It's better to get them disposed of, in Belgium at least. So then it's no profit. But if you go to a couple of thousands of tons, it becomes interesting. Another aspect is the availability of off-site treatment centers. In some countries, like in the Nordics or in South America, the distances are very significant, and then your transport cost becomes the key cost factor. Then even for smaller amounts, it can be very beneficial to do it on site, but of course then the cost price will be a bit higher because your general cost and installation costs needs to be flattened out to or needs to be calculated back to a limited volume. Okay, thank you. So we got a lot of questions about getting a copy of the presentation and the registration. You can email one of us and we'll be glad to send them to you. Also, please do not forget to fill in the survey and send it back to us. So I also want to remind that this was the first webinar. We already planned other webinars in the coming 2 Wednesdays. On the 8th of April, John Dyke, our R&D manager, will talk about proven bioremediation on exotic contaminants like polyols, MTBE, DCA, dioxane, chlorotoluene, and chloroform. Then on the 15th of April, we'll discuss about how remediation and redevelopment can go hand in hand. So we will discuss project examples of contractual, financial, and technical solutions to enable redevelopment of site in Belgium and in the Netherlands. If you didn't register yet for these 2 webinars, don't hesitate to send us an email or fill in the form. So thank you again for joining us, and we wish you to see you soon.
Thank you very much. Bye-bye.